asteroid impacts that rain death from the sky. Entire planets colliding and turning worlds into dust. A black hole that's been blowing away the rest of its galaxy for 100 million years. And massive stars that rock the universe like nothing else. Get ready to be blown away in a countdown of 10 of the largest explosions in the cosmos. These are the biggest blasts in the universe. They can not only wipe out cities filled with millions of people in the blink of an eye, but can lay waste to entire continents, planets, and even rip galaxies apart.
The universe is filled with tremendously violent explosions and blasts and events. The calm serenity of life on Earth is, to some degree, the exception, not the norm.
And whether they're massive collisions or explosions of entire stars, they all have important elements in common.
Really, another way to say explosion or blast is just a big liberation of energy all at once. When you liberate a lot of energy in something that already has structure, you tend to demolish the structure, so it seems very destructive. But the laws of nature will take energy and reconstruct it into some other form.
In 1994, more than 20 pieces of the Shoemaker-Levy 9 comet pummeled Jupiter.
There were big black scars all across the face of Jupiter, so large even that they could be seen clearly even with amateur telescopes.
The largest comet fragment was more than a mile wide, and the force of its impact was equal to 6 million megatons of TNT.
That's about 100 times or more of the entire nuclear arsenal of the world. So if you took every bomb in every corner on Earth and exploded it in one big explosion, you wouldn't even begin to touch the power of this fragment colliding into Jupiter.
But guess what? Even that type of power isn't enough to qualify as one of the biggest blasts in the universe. The first event to make the top 10 was many times more devastating. Number 10, death from the sky. The smallest blast on our list may still have been big enough to wipe out the dinosaurs by blocking out the sun with smoke and debris. It's the Chicxulub impact, the asteroid that crashed into Mexico's Yucatan Peninsula about 65 million years ago. A 6-mile-wide space rock, taller than Mount Everest and almost as wide, thundered into Earth.
So I'm sitting in front of the meteor crater in Arizona, and this is about 3/4 of a mile wide. So if we were to drive across this at about 55 or 60 miles per hour, it would take like a minute. Well, the crater created by the asteroid that impacted the Yucatan Peninsula, it would take over 2 hours to drive it at about the same speed. So you can imagine how much larger that crater is than this one behind me.
The 112-mile diameter crater is big enough to fit New York City, Philadelphia, and everything in between inside. If it struck today, about 12 million people would be killed instantly, not to mention the damage and casualties that would spread beyond the crater. That's because the energy in every blast is released in several ways, such as light during the blinding flash of the impact, and heat, capable of spreading wildfires across much of the globe, But with collisions, most of the devastation comes from the energy of motion, known as kinetic energy, which creates the crater and the flying debris.
The energy in the impact that created the crater at Chicxulub had to have been enormous, probably about 250 million megatons. That's a lot of energy. The largest bomb ever exploded on Earth was 50 megatons. So that compared to 250 million gives you a sense.
It was also about 40 times greater than the energy released by the largest Shoemaker-Levy 9 comet fragment to hit Jupiter. And figuring out the kinetic energy released in a huge asteroid impact is all a matter of plugging some very big numbers into a simple equation.
The key thing to keep in mind when considering the energy in these kinds of collisions is that the formula for what's called the kinetic energy, the energy of motion, is a half mv squared. The mass, and then the square of the velocities.
Mass is the weight of the object, and velocity is the speed it's traveling.
You can have a huge amount of energy for a massive enough or fast enough object.
Considering that the Chicxulub asteroid weighed nearly as much as Mount Everest and was moving at over 50,000 miles an hour, about 50 times faster than a bullet from a revolver, it's no wonder it was one of the biggest blasts in the universe. But what about its effect on the structure of the entire planet? An explosives expert places a small charge just under the skin of a watermelon to simulate the type of energy released when this asteroid slammed into Earth.
As you can see, something that would be devastating to us is not too devastating to the planet as a whole.
So there's still plenty of room for the blasts to get bigger. Number 9, Martian impact. Luckily, Mars, and not Earth, was the target of an asteroid 200 times larger than the one that slammed into the Yucatan Peninsula.
The asteroid that impacted Mars about 3.9 billion years ago was 1,200 miles wide. Now, that's about the size of Pluto. And if you imagine most of the continental US, from Denver to the Florida Panhandle and Chicago down to the south of Texas, huge.
And that's just the size of the asteroid. The crater, known as the Borealis Basin, is another story. The hole covers about 40% of the planet.
So the Borealis Basin on Mars is about 5,300 miles wide. Now the crater behind me is not even a mile wide. So you can imagine multiplying this by over 5,000 times, and that's the size of the impact crater on Mars. That's about the size of the continent of Africa. Amazingly huge.
While the speed of the asteroid that smacked Mars wasn't much different than the one that hit the Yucatan Peninsula, the mass was many times greater, leading to a much larger release of energy.
Probably about 1 million times more energetic. So it would be about 250 million megatons of energy. And that's a lot of energy. And that's why you got such a big, big basin.
Something like that hitting Earth today would put the instant death toll in the billions and would probably wipe out all life on the planet soon after. But the next blast did blow an even bigger chunk of crust off our planet, luckily before life even existed here. Number 8. The Big Splat. Instead of Mars being a target, imagine an asteroid the size of Mars slamming into Earth. Most planetary scientists believe that's exactly what happened soon after the Earth formed about 4.6 billion years ago. It's known as the giant impactor theory, also nicknamed the Big Splat.
The early solar system was a much busier place than it is today. Basically, it hadn't settled down yet. So there are lots of fragments running around, producing all sorts of collisions, which ultimately produced the bodies we know today.
Earth was still a molten wasteland, devoid of life back then, which is a good thing, since the force of that collision would have ended life in its tracks. So how did the planet recover from the most violent event in its history? Many of the biggest blasts in the universe are caused by comets and asteroids slamming into planets. These impacts can unleash hundreds of times more energy than the entire nuclear arsenal on Earth. But number 8 on our list is even more powerful than that. A blast caused by a rock the size of a planet slamming into Earth. It actually happened soon after the Earth had formed, about 4.6 billion years ago, when an object the size of Mars, sometimes known as Theia, slammed into our world with catastrophic effects. Compared to the Pluto-sized asteroid that smashed into Mars, the Mars-sized rock that nailed Earth was more than 3 times larger, releasing much more kinetic energy.
The Theia impactor that knocked off the crust of Earth was probably about 10 times more powerful than the Borealis Basin impactor.
But this incredibly destructive force also had some very important benefits.
So when Theia impacted the Earth, it happened probably at a glancing blow. And in doing so, the iron cores of the 2 planets actually melded together and formed a larger iron core and a larger Earth. Now, Theia's mantle probably got completely blown off in this impact because it's a little smaller than Earth, and some of the Earth's mantle got blown off. So you have all this mantle debris floating around, orbiting, and it actually coalesced to form the Moon.
The Moon stabilized Earth's axis, preventing it from tilting wildly, which keeps Earth's climate steady. It also slowed Earth's rotation over time to the 24-hour days we have now. Once again, to simulate the power of this blast, an explosives expert places a charge on a melon representing Earth. Could this be the one that blows the melon away?
Even though there's a lot of damage, the basic structure is still intact.
With the heat of the impact, the Earth and the debris were both molten. And that molten state is the reason why the impact didn't leave a massive crater behind. The molten Earth reformed as a sphere and eventually cooled. So is there any kind of impact that can turn a planet into dust? Number 7, when worlds collide. Deep in space, 2 planets, one the size of Venus, the other Earth, are on a collision course. They're rocky planets, possibly even harboring life. Something in their solar system has pulled them out of their regular orbits, and instead of a glancing blow, they smash together in a head-on collision. Anyone standing on those planets would have witnessed a terrifying event.
You can imagine if you had a direct view of the planet moving toward us. That means the sky would quickly fill completely with this planet about to impact, and then it would be over like that. It would be such a rapid extinction of life that you probably wouldn't have time to think about it.
This isn't some fictional doomsday scenario. Some researchers think this massive blast rocked the cosmos within the last 1,000 years. in a binary star system about 300 light-years away. It's known as BD plus 2307 in the constellation Aries.
It has a tremendous amount of dust in it. 1 million times more dust than in our solar system. We think that this dust may have been produced by the collision of two planets, roughly the size of the Earth and Venus, just head-on, whack, shattering each other, producing a tremendous amount of dust.
It takes enormous amounts of energy for two planets to pulverize each other into dust. Now, instead of hundreds of times the world's nuclear arsenal, we're talking millions of times or even billions of times that energy. With this even larger charge, we're not just going to break off a chunk of this melon, we're going to blow it to smithereens.
But as terrifying and destructive as planetary collisions can be, they're still much smaller than the different types of blasts that come from stars.
It's a whole new ballgame. The main reason is that there's a lot more mass in a star than any planet-sized object. And then there are all kinds of mechanisms that can take place involving nuclear fusion or various processes that involve gravitational collapse, which can drive a lot of energy as well.
One of these energetic blasts is number 6 on our list, magnetar flares. Magnetars are rapidly spinning neutron stars, which form when stars several times larger than our Sun begin to die and collapse in upon themselves. Imagine if our 865,000-mile-wide Sun suddenly compacted to the 12-mile length of the island of Manhattan. All of that matter is condensed into something so dense, it's estimated to be 10 billion times stronger than steel.
To give you an idea of how incredibly dense neutron star material is, if this cap was filled with neutron star stuff, it would weigh 100 billion tons on Earth. More than this hill, as much as an entire mountain.
The magnetar name comes from the fact that certain neutron stars, for reasons that are still unknown, have the strongest magnetic fields in the universe.
The magnetic field of a magnetar is exceptionally strong. It can be 1,000 trillion times as strong as Earth's magnetic field. That's fantastic.
The magnetic fields are so intense that if a magnetar suddenly appeared halfway between the Earth and the Moon, it would be strong enough to disrupt all of the electronic equipment on the planet, including stripping the information off every credit card on Earth. And the reason magnetar flares are so powerful is that the magnetic fields around certain areas of the star sometimes twist themselves so much that they can't twist anymore, and suddenly release like a spring.
The process is similar to a solar flare in that it's the magnetic field that's giving rise to the energy. It's the shaking and tangling and sometimes the reconnection of lines of force going in different directions that gives the energy that powers the flare.
But unlike planetary collisions, where kinetic energy dominates, magnetar flares shoot out most of their energy as electromagnetic radiation. In other words, light. And one magnetar flare in particular was strong enough to blind satellites orbiting Earth from 50,000 light-years away. The biggest blasts in the universe dwarf anything we can imagine on Earth. We're already billions of times beyond the entire nuclear arsenal of the world. Number 6 on our countdown are the flares that burst from incredibly magnetized neutron stars, known as magnetars. And one of the most powerful ever observed from Earth released as much energy in just over 1/10 of a second as our sun does in about 100,000 years. The blast in 2004 came from a magnetar known as SGR 1806-20 in the constellation Sagittarius. It's about 50,000 light years away from Earth on the far side of the Milky Way.
It was incredibly powerful. All that energy came in 1/10 of a second. It blasted the detectors and satellites that happened to be flying around up there. In fact, it was the brightest blast ever seen from an object outside our solar system. And yet, it was 50,000 light years away.
But what does brightness have to do with the power of a blast?
So I'm standing in a dark room here, and now I'm going to turn on a light bulb. How bright that light bulb appears to me depends on 2 factors. It depends on how intrinsically powerful or luminous the light bulb is, its wattage, how much energy it puts out per second, and it also depends on the distance of the light bulb from me. When I'm close to the light bulb, I see that the light bulb is bright. If I move a factor of 2 farther away, then in fact it looks a factor of 4 fainter. That's the inverse square law of light. The power of the light bulb has remained the same, but by being twice as far away, I get only 1/4 of the light reaching my face and my eyes. Astronomers measure the apparent brightness of the star or the explosion. They figure out its distance through some other technique, and from those 2 variables, they figure out the power or the luminosity of the source.
That light is released not just in visible wavelengths, but across the electromagnetic spectrum. And anytime researchers detect gamma rays, like they do in magnetar flares, they know it must be a big blast.
Gamma rays are a type of light, but a much more energetic light than we see with our eyes. So the spectrum of light that we're familiar with goes from very low energy and through the visible part of the spectrum, the light that we see, all the way out through X-rays into this extremely high energy component of light, which is called gamma rays.
Even a 1/10 of a second short gamma ray flare, like SGR 1806-20, would still be able to fry the Earth with radiation from many light years away, as long as the full force of the flare was aimed at Earth. But not all of the biggest blasts in the universe are over in a fraction of a second. Number 5, the 100 million year blast. 2.6 billion light years away from Earth, a supermassive black hole, billions of times the mass of our sun, has been wreaking havoc in the center of a cluster of galaxies. Known as MSA 735, it's been shooting out 2 continuous jets of particles in opposite directions. Scientists believe the jets have been raging for the past 100 million years, punching 2 huge bubbles into the surrounding galaxies.
MSO 735 really is the prototypical example of a black hole blowing bubbles. What we're seeing here is giant cavities being evacuated by these powerful jets. So they transport vast sums of energy down from the black hole out to huge distances, maybe about 1 million light years or so.
1 million light years is 10 times wider than our Milky Way galaxy, which means these jets are powerful enough to create 2 very big bubbles.
The total energy within these 2 bubbles is stupendous, far exceeding any other amount of concentrated energy that we know of in the universe. However, it must be remembered that the energy was released over 100 million years. That means that per unit of time, the total amount of energy released wasn't all that big.
Still, the jets are strong enough to shoot the particles out at millions of miles an hour, about a quarter of the speed of light. The jets and resulting bubbles only come from about 1% of the most massive black holes in the universe. That's because the forces near these monsters are so huge that instead of swallowing everything, they actually end up pushing some particles away.
It's important to emphasize that these giant explosions are not the explosion of the black hole itself, but rather an ejection of particles from near the black hole, the vicinity of the black hole. By colliding with one another, they can, in some cases, be ejected out of the vicinity of the black hole.
But how can this two-sided blast possibly keep going for 100 million years? It's all a matter of how much cosmic stuff is available, as planets and suns are stretched and ripped apart down to their very atoms and drawn towards the black hole.
So these jets that we've estimated have been going on for about 100 million years still have a huge amount of fuel available to them. That process can go on for an extremely long time, hundreds of millions of years.
Now, imagine taking a big chunk of that energy and releasing it in less than 2 seconds. That's what researchers believe happens in blast number 4, short gamma ray bursts. Gamma ray bursts are more concentrated than magnetar flares.
It's a concentrated beam of radiation, like a laser beam. It comes out as a narrow stream.
The gamma rays in the beams are also traveling much faster than the particles coming out of black hole jets.
The observations show that the energy is coming out in jets, moving at very close to the speed of light, 99.9999% the speed of light.
At that mind-bending speed, in just a few tenths of a second, short gamma ray bursts can release as much energy as our sun does in millions of years. But for years, scientists couldn't figure out why some gamma ray bursts were long, lasting many seconds or even minutes, while others were usually only a fraction of a second. Then, one burst in 2005 led researchers to an exciting new theory about incredibly dense neutron stars annihilating each other. The power of man-made atomic bombs is nothing compared to the galaxy-rattling explosions in the cosmos. As we continue counting down 10 of the biggest blasts in the universe, these cataclysmic events are now producing as much energy as our sun does in millions of years. Short gamma ray bursts are number 4. For years, scientists have been confident of the source of long gamma ray bursts, those that last over 2 seconds and sometimes erupt for many minutes. They come from galaxies with massive stars. And when certain massive stars die, they collapse and then explode, blasting out incredible amounts of energy as concentrated jets of gamma rays. But in 2005, detectors in space captured a powerful gamma ray burst that only lasted for a fraction of a second.
This was very exciting because all the gamma ray bursts we'd seen before were of the different variety, longer, coming from galaxies where massive stars were dying. This was something different. It was short, and it came from a region where no massive stars existed.
This burst came from a galaxy thought to have some incredibly dense neutron stars in binary pairs that orbit each other. And scientists believe that the only way to generate such a quick and powerful burst of gamma rays is if two neutron stars engage in a deadly dance, orbiting closer and closer, then finally crashing into each other. This is thought to be the moment when a black hole is born.
When the two neutron stars finally touch, one of the neutron stars gets shredded into a disk, and the thing that's left is too big to be a neutron star. There's no force in the universe that can hold up two neutron stars, so it collapses to a black hole.
The 2005 event, known as GRB 050509b, since it was the second burst to occur on May 9th of that year, was the first short gamma-ray burst whose location was pinned down. It didn't look very bright from Earth, but that's because it was an astounding 2.2 billion light-years away.
GRB 0509b lasted only about 40 milliseconds, but in that time, it released about as much energy as the Sun will release in 100 million years.
But the power of colliding stars can't compete with the even larger amount of energy released when an entire star explodes from the inside out. Number 3, supernovas. When large stars die, they don't just fizzle out like our sun eventually will. They go out with a bang. There are actually several types, but the two main ways a supernova explosion happens is either when one star in a binary star system swallows part or all of its companion, or when a supermassive star collapses in on itself and ejects its outer shell in the process. Either way, a mind-boggling amount of energy is quickly released.
The energy of motion, the kinetic energy of the ejected material, can equal the total amount of energy that the Sun will release over its entire 10 billion year lifetime.
The binary star type of supernova is similar to a hydrogen bomb, where runaway nuclear fusion leads to a massive explosion. These are known as Type 1A supernovas, and in 2003, one of these blasts flooded the cosmos with more light than an entire galaxy of stars combined.
It was over 20 billion times more luminous than the Sun for about 2 weeks, and this all came from the explosion of something not much bigger than the Moon, about 1.4 times the mass of the Sun, from a thermonuclear explosion from fusion.
For the core collapse type of supernova, an incredible amount of power is generated when the outer shell slams down and gets an extra kick from the denser core of the star.
Imagine this ping pong ball represents that outer, lighter material of the star, whereas this superball represents the heavy inner core. You can see that the ping pong ball actually doesn't really bounce that much on its own, and there's the bounce of the superball. But what you'll see is that when I send them down together, the bounce of the superball back up will propel the ping pong ball much higher. And that's very much like what happens in the supernova, where you have the heavy inner core bouncing back out and meeting that lighter material and blowing it out.
In fact, one supernova explosion in 2005, known as SN 2005-AP, flashed brighter than all of the others for weeks on end. But it didn't do any damage to Earth because, luckily, it was also 4.7 billion light-years away. And like many of the other blasts on the top 10 list, supernovas don't just destroy.
A supernova is a little bit like a recycling center. There's a lot of material in those massive stars. It's anything from 8 times to over 100 times the mass of our sun. So there's a lot of material that's going to be processed in those stars, just like there's a lot of raw material here at the recycling center that's going to be processed.
The matter in the universe is dominated by light elements like hydrogen and helium. But the inside of a star about to go supernova is the main source of the various metals and other heavy elements we depend on for life.
Just like these materials are being sorted into different categories, the star starts to process heavier and heavier elements, starting with hydrogen, then helium, making heavier and heavier elements all the way up to iron when the fusion process stops. Later on in its life, when it becomes supernova, with the aid of the compression effects in the supernova, the star will make even heavier elements. Just as these materials are now packaged and processed and ready to leave the recycling center and go out into the world to be reused, the materials that were made in those stars, that were then finally cooked and blown out into the universe by the supernova process, those will be reused as well. They may be used in other stars or perhaps other planets. The materials that we're made of here on Earth, the materials even in our bodies, those heavy elements were made in supernovae.
While supernovas are massive explosions themselves, they can also trigger secondary blasts with even more concentrated energy. Number 2, long gamma ray bursts. The long gamma ray burst comes out of the most powerful supernova explosions. They're as strong as the short gamma ray bursts, but since they last much longer, anywhere from 2 seconds to nearly half an hour, they blast out much more energy overall.
The long gamma ray bursts are completely different beasts compared to the short gamma ray bursts. They're immensely more powerful, maybe up to around 10,000 times more powerful than the short duration bursts.
These concentrated jets of energy only come from supernova explosions involving stars 30 or more times the mass of our sun. And just like the short gamma ray bursts, they're evidence of the birth of a black hole.
Long gamma ray bursts are, in some sense, a variety of hyperenergetic supernova. The iron core collapses as before to a neutron star, but too much material falls down on it and it can't stay a neutron star. The temperature rises to 10 billion degrees. The luminosity in 1 cubic inch of this is as big as the sun. And this power can't flow out in the equator. It gets focused like in a shotgun blast out the rotational axis of the star.
So how much energy do the most powerful long gamma ray bursts release compared to our sun? The answer is shocking. We're at number 2 in our countdown of the biggest blasts in the universe, long gamma ray bursts. They're the most powerful concentrated beams of energy in the universe. They release many times more energy in a matter of seconds or minutes than our sun will produce in its entire 10 billion year lifespan. The key to their devastating power is focusing that energy in a narrow area. A firearms expert illustrates the point with 2 different shotguns. First, a shorter gun, where the shot spreads out quickly after leaving the barrel, unlike a gamma ray burst.
As you can see, there's some damage to the melon, but not that much because the shot was spread out and only some of it hit the target.
Now our firearms expert is switching to a longer barrel that keeps the shot concentrated in a tighter pattern as it goes down range. The same effect as a gamma ray burst.
Concentrating the shot can be devastating. It's a good thing for us that most gamma ray bursts are millions or billions of light years away from Earth and are pointed in the other direction.
It's believed that these concentrated jets shoot out when massive stars collapse into black holes. And in 2008, scientists detected one of the strongest gamma-ray bursts on record, known as GRB 080916C. It lasted an incredible 23 minutes.
This GRB was one of the most exciting blasts ever seen because the total power inferred from the observed brightness and the distance of the blast exceeded that of any other known GRB up to that time. Moreover, we can tell that energetic particles were blasted out along two jets at 99.9999% of the speed of light. GRBs are so powerful along the beam of particles and radiation that even ones that are thousands of light years away, but pointing at us, could destroy much of the life on Earth.
But if long gamma-ray bursts are the most powerful explosions in the universe, then how could they be number 2 on our list? Because the top spot goes to something that didn't happen within the universe, but happened when the universe itself was formed. Number 1, the Big Bang. This mother of all blasts is technically an expansion and not an explosion, since it was not a blast within a defined area.
It wasn't an explosion that happened somewhere in space. It's all of space. It's the actual fabric of space-time itself coming into existence. So in the concept of a biggest blast, it's as big as it gets. It was the whole universe blasting into existence.
And the speed and temperatures of the Big Bang dwarf anything that happened inside the universe once it was formed.
Those temperatures are beyond anything we can imagine. There are trillions of degrees if you measured it in usual units. So compared to any explosion, say here on Earth or a star or what have you, this is well beyond that.
Researchers believe that theoretically, they can go back so close to the moment the Big Bang happened that a fraction of a second doesn't come anywhere close to doing the timescale justice.
The bang of the Big Bang is a time in the early universe known as inflation. The size of the universe went whoosh. It just expanded so quickly, doubled in size many times over a very, very short interval of time. This incredible inflationary exponential state of expansion lasted only a tiny fraction of a second. A millionth of 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 a second.
During this early expansion, it seemed as if things were moving faster than Einstein's universal speed limit, the speed of light.
In fact, it expanded so quickly that it was faster than the speed of light. That's okay. That doesn't violate Einstein's theory of relativity. Space itself can expand faster than the speed of light. No particle can travel through space faster than the speed of light, but space itself can and does expand faster than the speed of light.
And the Big Bang is the largest reminder of all that the biggest blasts in the universe, these sudden releases of energy, do much more than destroy.
The creation of our universe, the creation of the sunshine that comes out of stars, and the creation of our own moon all came from this tremendous liberation of energy all at once. So there's a very intimate link between matter manifested in one way and then being destroyed and then re-emerging in a new way. And, you know, here on Earth, it re-emerged as us.
And as the universe evolves, its biggest blasts will continue to be both the destroyer of worlds and the creators of new possibilities.